we kind of all went with with Shakespeare's themes, kind of going for talk descriptions. So I went with Puck's Wild Pansy. If you're not familiar with A Midsummer Night's Dream, Puck's Wild Pansy makes people fall in love. So the idea is that data visualization will possibly help you fall in love with your network data again. If you've never heard a talk from me, I'm a data scientist with NARI. It seems like a forever PhD student at this point with UCCS here in Colorado. I have quite a few prior lives. I did a stint in the service where I was a nuke for the Navy. I worked with Hack UCF and now do a lot of volunteer efforts with B-Sides Orlando, DEF CON, and KernelCon. If you've seen the B-Sides Orlando graphic there in the corner, that's something I did last year. So if you don't get anything from this talk, these are my major takeaways. There are different types of data visualization options for different use cases. And honestly, it's the same idea for most machine learning. No free lunch. It means that if you want more control and you want cooler stuff, you have to do more work. But this is getting easier, and I'll kind of go into that. So I'll go through the motivation for this talk, some visualization libraries in Python, feature selection and processing, something that I have to go through kind of frequently. And then I'm going to go through a couple of Jupyter notebooks to kind of bring this point home. As I said, I'm one of those poor PhD students. I need to sort network data. It's for my dissertation. So my budget is 0. And my network traffic captures tend to be over 500 megabytes. If we're talking like the raw PCAP, I have baselines that are 6 to 7 gigs a piece. I could probably, if I really wanted to, chunk them into pieces and then bring it in sequentially over days if I really wanted to. But no, I'm not. That's not me. I didn't really need real-time dashboards. This is point in time, so it's not continuous, right? So I don't need to know how this is going on over time. It's just a solid PCAP. I need to visualize that data. I need to visualize data about that data, particularly through feature selection and machine learning. And then finally, I have to communicate this to other people, right? I have 2 research advisors that, well, to be frank, if I didn't have it in a blog, they would probably forget that it happened. So yes, communicating to stakeholders is what's really important to me. And right now, there are several ways that this is done, right? I've asked several people what their workflows look like for looking at PCAPs. Some people say, I just throw it into Splunk. There's PCAP Analyzer for Splunk. And then there's the Splunk ML Toolkit, right? These are apps that come into Splunk Enterprise. And as you see here, they produce like dashboards, pie charts, alerts, what have you. You could have an Elasticsearch stack where you have Logstash, an ML node, and Kibana, and they all play with Elasticsearch. And again, you get like these really pretty dashboards. A lot of these are already set up for you. So if this is like your use case, this obviously sounds amazing because it's like, oh, I just get my PCAP data in there and pretty graph spit out. Maltego, another way. Here we see another kind of network diagram where each one is kind of specific to the device and to like a specific GeoIP location. And of course, this works at varying degrees of complexity. You could take a PCAP and bring it into Grass Marlin, which I was informed it's all in caps for that project name, that's fine. And you can get out some reporting. You can get out CSVs and an SVG that kind of looks like here at the bottom, where you get a network diagram. It doesn't look pretty. And there are some very cool icons here. If you like look in, you can see infrastructure or workstations that Grass Marlin kind of populates for you in this graph. And again, varying degrees of complexity. You could always write your own. You could write a Lua script with T-Shark and use GraphViz to kind of populate your own graphs. And I pulled this out of Wireshark for security professionals. So I'm not going to go over any of those. I'm going to go over Python. And here I kind of have it set up in a stack. It's not really a stack. It's kind of 4 areas of libraries that intermingle with each other or rely upon each other to plot. And that particularly is in like the Seaborn Matplotlib association. But here you have your base language, Python, IPython. IPython is providing the environment which you can view code on Jupyter. And then you can manipulate data either through NumPy, and then there's SciPy, but I'm not using it for this particular example, pandas, and scikit-learn. And then you want to visualize like all of that manipulation that you do through Seaborn, which has all these pretty colors, and palettes, and Matplotlib, which is really kind of doing all the strong arm work behind the scenes. So right, as I said, Seaborn, it's built on Matplotlib. It's closely integrated with Pandas data structures, and it's got these really cool palettes. I'll show those here in a second. And then Matplotlib mostly works, or most of it that you see is through PyPlot, and it's Python's main plotting library. I will also kind of show NetworkX, which does graphing more for the network science crowd, so like nodes, edges, but you can use it for IP graphing. There's a little bit of the notebook that has that in there. And then Bokeh, which I didn't really have time to show, but if you wanted to make interactive visualizations, kind of like the D3JS-esque, you could do that through Bokeh. If you were trying to follow along and like how on earth do you get these visualizations through PCAT? Well, generally you convert it to CSV. If you do it through Wireshark, what you see right there is exactly what you're going to get out of T-Shark. Not a whole lot of information. What PCAT number it is, looks like a timestamp, a source and destination IP, the protocol name, what port it was over, and then kind of the sequence, ACK and window. Personally, I use something called Kickflowmeter. It is an open source program out of the University of Canada. I want to say, I'd have to look it up. But on their site, they have the Kickflowmeter. If you wanted, you could use Joy, which produces more net flows than really CSV, or you could write your own. And most people that I know don't have the patience to write their own PCAT parser, but it's open there if you'd like to. You need these particularly for feature selection and processing. I saw this on Twitter. It was totally relevant to what I'm trying to speak to here. You realize that you're better off with Sysmon and Elk than with $2 million Steam license quota filled with Firelog data. And what I'm trying to bring home here is that feature selection and processing is extremely important if you don't want to waste your budget on storing data that isn't actually useful. Right, so choosing which features to keep can save disk space and processing. Last time I checked, that's also known as money. Network data tends towards a higher number of features, right? Higher feature space. Kickflowmeter itself produces 80 features from a PCAP. And when I said data about data, a lot of it is metadata. So min, max, standard deviation, features about features. And realize that if you are training a machine learning algorithm, right, using these features, if you have irrelevant features in there, it might affect the training performance. So not only to save time, money, processing, your accuracy may be brought down if you are keeping in features that are irrelevant. If you're not familiar with feature selection, I'm not talking here specifically about dimensionality reduction, which is to kind of remove pieces that, or remove features, rows, et cetera, that do not really hand the classifier the best way to classify, I'm using classify in this case, the data. Particularly, I'm speaking about supervised and unsupervised feature selection. And there's intrinsic wrapper and filters that kind of fall under supervised. Trees like random forest would be under intrinsic. So this would be like a machine learning algorithm that you run it, and then by its own nature, it tells you which features it prioritizes. So like random forest would be here. A wrapper, which is essentially a program around a core algorithm like a random forest that uses that classifier to determine feature importance. And then there are filters, which has like statistics or like a feature ranking, feature importance ranking in order to determine which filter or which features you want to keep. For the purposes of this talk, I'm just going to cover visualization using RFE. RFE, right, of course, recursive feature elimination. Most people are like, what the hell are you talking about? Hold on. As I mentioned, it's a wrapper method. It's a different ML algorithm is used at the core of the method, right? And as I said, it's wrapped by RFE. I mentioned before random forest. You could also have decision tree and gradient boosting. And the idea is that it works by searching for subsets of features, starting with all of the features, and then it removes features until the desired number of features that you choose remains, right? So the core algorithm, I believe this time I'm using random forest, it'll rank features by importance and then discard the ones at the tail and then refit the model based on what features were kept. The data set that I'm using in these Jupyter notebooks is something called CTU13. It is a botnet data set generated by Garcia et al. If you go to the link here, you can find more information about this data set. But essentially, they populated a botnet and watched over the network as different types of bots, ferried their traffic or attacked different nodes. If you are looking for it, you can find all of these here on my blog, and that's where I'm going to now go. Hopefully I didn't lose anybody here. Let's see. Let's see, I see that I am not quite there yet. Let change the screen. Yes, this one. Wonderful. All right. So here is a visualization. If you're not familiar with this is a Jupyter notebook. I basically pull in the botnet that I have already processed over into a CSV using Kickflowmeter. If you bring in the data frame, it kind of looks like this. You'll notice there's like a flow ID and a source and destination IP, and basically all the other things you would find in a data set, right? At least for PCAPs. So for these visualizations, I'm basically trying to go through and find things that you would normally put in like a Splunk dashboard, but instead of, launching Splunk and pulling in my PCAP, essentially I'm pulling my PCAP into Jupyter and running these same data visualizations. This is more convenient if I have a large number of disparate data sets, which for me, it was easier to analyze using Jupyter than instead of bringing them one by one into Splunk and then trying to analyze them. So here, and this is Seaborn, but notice that it is using PLT, PyPlot, which is part of Matplotlib, in order to do the heavy lifting. The palette here is Blues D, so I didn't have to choose any of those colors. They were generated for me. Essentially, I bring in the data frame. This particular data set has something over 100 IP addresses from the source. So here I'm just taking the top 10 and graphing them here as part of a bar plot. Similarly, I can do that as part of destination IPs, so like who's sending the most data. Here you'll notice the palette is something called colorblind. So if you have people on your staff that have trouble differentiating the different types of bars, you want to be more accessible, this already has a palette for you. Similarly, you can visualize the protocols. This goes by the IANA assignment. So here TCP is 6 and UDP is 7. Similarly, we could rail plot or kind of scatter plot any of the ports that are used. Obviously, this is quite the spread across ports, but notice that there are quite a bit concentrated around 1024. If I remember correctly, it's around port 80 because there's a lot of HTTP traffic. And now here I'm going to show network X. Here I've kind of have it in line. If you generate it from Python, it's actually more of an interactive plot where you can move the nodes around. But here in line, it's just this. But notice that if this were overloaded with IP addresses, it becomes more and more challenging to get them to not fall on top of each other and actually see them. So this is better for smaller networks. I wouldn't say probably over 200 nodes. All right, let's see if I can get this to switch over. Here we go, yes, all right. Just for funsies, we were kind of looking at, if you're familiar with Jack Daniel from B-Sides, he did a survey on degrees in education and cybersecurity. Here I am just taking in his CSV. I kind of renamed his titles for his features because they were very sloppy and very hard to kind of do data analysis on. But here it's the same idea, only now these are more of categorical responses instead of a numerical feature. So here the question was, do you have a security role? You see over 300 responses are yes, several are no, several are tech, but not security. Same idea using the colorblind palette. You'll see that most of the respondents had a bachelor, a good deal had master's, some had doctorate, and some, actually quite a bit, had some college, but no degree. If you want to play with or look through these visualizations more, you can come up here to this address, and I have them posted on my blog. Additionally, if you want to just play with the Jupyter notebooks, I have them kind of shoved into my GitHub. All right, so let's see, what were the interesting ones, if I remember correctly? Oh yes, some of these, like what was the question itself? Degree fields. It turns out everybody in InfoSec comes from very different places. And I'm not sure if I'm going to be able to view image, perhaps. Here we go. Of course, this is a very large image, so you can't really see it there in line. Notice that people in InfoSec come from a very diverse crowd, but from the most part, this would say most of them are computer science. Of course, some of these need to be deduplicated, but notice that these are quite a disparity of different degrees. And you can visualize all of this in Seaborn. Let's see. Lastly, I wanted to cover RFE. And notice that if you are maybe doing analysis, again, of data about data, you will kind of need to have the hooks to visualize that. Originally, I was going to show Baruda. Baruda is a statistical feature selection algorithm. It was brought into R originally and ported over to Python and adopted by scikit-learn. The problem with Baruda is that it doesn't necessarily have the hooks to visualize, so I can't show you cool things like this box plot down here at the bottom. Here, it shows you the different evaluations for the features, where they scored on model performance. So, right, these are kind of cool things to do that you might not really get out of Splunk. I haven't used their ML app. So if somebody wants to prove me wrong, I'm totally all ears and love to learn about that. But as far as I know, no. All right. So references for this talk. I pulled a lot of information, particularly RFE, from data preparation for machine learning. from Jason Brown Lee. If you have been to, I believe it's Data Science Mastery, he has a whole site on basically how to do what I'm talking about right now. And it's been really awesome to kind of look at the things that he just gives out for free. So when I was saying earlier, one of the takeaways from this, right? One of the takeaways is that this is getting easier. So I did show all of these huge blocks of code. When I was first starting out, they would have been very daunting to try to go in, learn how it all works, and then try to edit it to see, to like experiment, and then try to bring in my own code, which usually explodes. So going through and looking at how other people have done these visualizations is getting far easier to understand, to use the API, and to like use it on new sets of data that haven't been coerced and massaged to give you like the pretty graphics. I mentioned CTU13. They have a paper, empirical comparison of botnet detection methods. If you like more stuff about what I'm talking about as far as Jupyter notebooks, you should check out InfoSec JupyterThon. They just had it. It was really awesome. I'm referencing Jack Daniels' Uncommon Sense Security blog because that's where I pulled the survey data from. And of course, I was talking about Baruda. If you need the slides and code for what I talked about here, you can get them at this link right here. And I'm open for questions.
So far, we haven't had any questions. We've only had some input from one of our viewers that the colorblind component of that was awesome. Another nice comment from a viewer. Does anybody have any questions for Heather? I believe you're muted there, Stefan.
What even is technology? How do I fix that with Jupyter notebooks, Heather? Like, that's what I want to know. No. I think one of the things that are very difficult when you're trying to get into data science or when you're trying to get into these sorts of things is like getting started on the data sets, right? You obviously have quite a bit of background in this sort of thing. So like, what is your methodology for just getting started, for just diving into data and starting to tease things out? Because I think that's where most people start to fail.
Looking at it first. And this kind of, yeah, that sounds easy. Just look at the data. No, I mean, like, literally look at the data, pull it open, look at it. I actually like Excel. Don't kill me. But you usually have to cut up your data, right? So Excel only works up to really, honestly, 100,000 rows. And after that, you're taking a one-way ticket to Crash Town, right? So if you can like cut off or just like head the top part of your CSV and then pull that into Excel and look at it, that's usually where I start. And you kind of want to look at what your data actually includes. Are they categorical? Are they numerical? For us in security, it's always the question, what do I do with IPs, right? IPs aren't a numerical. They're categorical. They map to places. And more importantly, IP addresses can be spoofed. Are they spoofed in your data set? So like you need to ask yourself these questions when you're looking at like each data feature. And then after you've looked at it and you're like, all right, well, this is what I have. The next question is, what do I want? What do I want out of this data? What is it trying to tell me? What am I going to use it for? And I think that's a huge place to start, especially when you start exploring some of these data structures and data types.
So my question, like I've dug in some on the machine learning side, but for different purposes. My question is more around unstructured data and how to determine what it is, like what questions you should be asking, right? Like even coming up with a feature set when you're looking at unstructured data is so difficult, right?
Well,
How do you go about that? I mean, you talk about IPs from an InfoSec perspective, but you have a blob of data. What is it that you start to look at there? I know that's very random.
No. I hate to say that regex is your friend, but sometimes that's what you're stuck with, right?
Okay.
It kind of depends on.
All right.
It depends on how unstructured your data is, right?
Yep.
If so, once upon a time, I used to mine dark web data. So I would log into a darknet marketplace and basically scrape their site from Selenium. So when you'd get that data back, it's an HTML blob.
Yeah.
Right. You'd have to like pull out features to even use them. And that's what I mean. Like, it kind of depends on how unstructured your data is, because you might be resulting to regex.
Okay. All right. Well, then I'm on the right track, because that's what it came down to. I was like, well, yeah, it's just a random regex of different things, and then we can start to analyze from there. So, okay.
If it's like an HTML blob, like I mentioned, you might be able to use something like Beautiful Soup on it to like pull things out of it, and that would help, because there are some libraries that will pull out specific unstructured types, right? But if it's just like, here is a hex dump. Yeah, you're gonna need regex. Like I don't even know how you would begin. Frankly.
Yeah, I mean, some of that has almost been like size versus like the amount of data that's in each of the different instances, the amount of different characters, right? Some of that gets interesting, but again, like it depends on the questions that you want to ask, right? Like what you're trying to get out of it.
Absolutely.
So.
I have all sorts of feelings about parsing HTML with regexes, but
yes,
hey, I'm not looking at the data, right? That's usually the last tool in the tool belt is resulting to regex, but there's a reason why people result to regex.
Yeah, for sure.
Regexes have all sorts of failure modes and whatnot. One other thing though that I was curious about, especially once you mentioned regex, do you have like a tool belt of regexes that you keep around for things, or even just like a internal knowledge base for yourself that you like? Oh, I saw this. Therefore, last time I used this regex, and now I'm going to reapply the same thing. Like, do you keep that sort of thing around, or is it really like each investigation, each visualization is different each time?
Generally, each data set's different. I was having an issue, the Kick Flow Meter, they give you like data about data. There's something called flow packets and flow bytes. And coming out of the tool, you will get nans and infinities. What do you think visualizations do not like?
Yeah.
So it's like, how do I detect that that's there in my data? How do I pull that out? One of the things that, notice I said the last tool in the toolbox is regex. I personally like to pull it into Python and then use Python slicing. So especially if it's strings, then I can, read row out of CSV and then parse that row into the pieces that I need and then rinse repeat. Let's see, what is the largest data set that someone just starting can feasibly do on a laptop before they need some sort of cloud computing? Well, it kind of depends on what you're running, right? My go-to working laptop has 16 gigs, which is why I say that 100K rows is the ticket to Crash Town. But realize if you're running 4 gigs, that might be much smaller. What is the largest data set? It's kind of dependent on what you're running hardware-wise. Generally, my idea is you pull in 1,000 rows, see how well you go. If you crash, well, you can't do 1,000 rows. If it's really quick, right, you watch the way that your hardware responds. You might be able to up it to 10,000 rows, 25,000 rows. I'm not particularly one to just sell, hey, just put it on the cloud, mostly because cloud computing is expensive unless you happen to be a student and you have money to throw on hours for cloud computing time, which some do, but not everybody.
It's like that old saw that if you can fit things into memory, it's not actually big data, it's just data. Like and I think this is something that we always run into, right? Like what one person considers big data, or requiring a cluster or requiring Hadoop or any of those sorts of things, like another person would just be like, what? I have a 256 gig machine sitting in my data center. I just do all my processing there. What's the problem? Like, I don't need a cluster.
I mean, if you're working with that kind of hardware, then more power to you. Most of us don't.
Yeah, exactly. But it is a great question. Like, at what point do we really want to move on? And it really is like what fits in memory, and what sorts of what sorts of requirements do we have there? And actually, in that vein too, what sorts of limits have you seen with Python? Because I've seen Python fail in weird places too, especially with memory limits. And I know you work with Python quite a bit, so that's what I was curious about.
First of all, I'm going to make a comment about the big data, because you got me thinking here. Coming off the wire, raw PCAP, I mentioned some of my baselines were like 7 to 8 gigabytes piece. And remember, I was talking about, you don't want to save and process all that data if you don't have to, like, over and over again, because, that's time and money. As you do feature selection, you move it over to CSV and you cut things down. Here at, CTU 13, it's probably about 100 megabytes now, because it's gone from this huge portion with like payloads and all of these extraneous features, converted to CSV. So we cut off all the payloads, we cut off all that stuff, and then you do it more. So you have more feature selection where you like cut out the flags that are mostly zeros, or take it from a sparse, right, to compact. And you're saving a lot of space, right? What you're actually processing isn't 8 gigs. It's more like 500 megs, maybe, right? And that's a huge difference on time and processing power. So like feature selection, do it. It's great. Don't process things you don't need to. And then to answer your second question, Python. I was actually using Bruta last night. I've got to do things for my research advisor. And I had pulled in things with low memory being false. So when I pulled it in from CSV, it pulled in everything as a float 64, which, if you can kind of consider the space of float 64 versus like int 64, that's a lot larger. And frankly, some classifiers won't even use it. You'll have to concatenate down anyway, just to even use the classifier on that data. And so what I was noticing is that I'd have like my kernel failing. It would just kind of silently just stop working without actually failing and giving me an error. The kernel would just be gone, and I'd have to reconnect it and completely rerun my notebook. One of the important things to notice is that when you are using these classifiers, how big your data types are and how many features you have, because that will greatly change how long you're sitting there waiting for that classifier or regression algorithm to process.
We actually had another question come in. How do you handle data drift as your data formats change over time?
Data drift as data formats change over time. I assume that's from a question, or that's asking about changing from raw PCAP to like CSV or JSON.
Yeah, and they clarified with data format drift. So I think you're in the right vein there. But also, obviously, as you process things, as
you feature engineer, things change. Yes.
Right, exactly.
To be honest, planning on how to format your data is probably going to save you a lot of time in the long run. So you can have any change, right? So let's say you have your main PCAP, right? Your raw data, and you decide you were going to keep the last, I don't know, 50 features, and you're going to dump 30 of them. Well, those features are gone. So if you need those features back, you have to reanalyze your PCAP, right, to get the features back and continue analysis. That takes time and energy. So when you ask about like data drift, keep the old files because you might have to rerun them, frankly. And sometimes it's just easier to have a sanity check. Maybe you made a transform and you didn't document it very well. If you have the old formats and can do it again, you can prove to yourself, give yourself like the sanity check that yes, this is correct. This is the way it's supposed to be.
It's almost like someone just had an entire 45-minute rant about planning and all those sorts of things there. But no, I think it's a great question, and I think it's a great point, right? Like when we work in data science, when we work on these sorts of things, like keeping around our old formats and documenting our expectations and documenting what we're expecting and whatnot is a huge thing. And I think data scientists very often are not trained in those sorts of things too, or we think of things in like a REPL or Jupyter Notebook or those sorts of things, and not the longer term planning of data and how we consume it and whatnot over time.
I think it's also like not just a planning, but a process of applied machine learning. It's one thing if you have your straight and narrow data set you pull in and it's all perfectly, structured for you, and there are no nans or infinities, and every row has all of its data nicely filled out for you. That doesn't actually happen.
You mean the data doesn't just like rain down from the gods in a way that you can easily consume it every single time?
That is the new oil, but baby, you got to drill for it.
Yeah. And actually, that's an interesting point too. Like, and you and I have talked about this before as well. Like, what sorts of things do you do when your data format is actually the problem?
Ooh,
Yeah.
I'm sure a lot of programmers come across this too. Hey, it's in JSON. We need it in CSV.
Yeah.
Now go. Luckily, Python has a bunch of libraries in core that help out that a lot. So you aren't just trying to write your own parser from scratch most of the time. To CSV, I believe that's part of Python. It's helped me out a lot. And honestly, it wouldn't be nearly as attractive if I couldn't pull in data as nicely as you can with that. But to answer your question, like going from different formats, a lot of that tends to be manual if there's a library not even written for it. And sometimes you want it to be manual because there will be no library written for a specific parser to do the thing you want to do.
It's also interesting too, and it harkens back to what you mentioned there, keeping around old data sets, versioning things, making sure that those processes stick around is incredibly important. Are there like techniques or are there mechanisms that you use to help manage your data sets, like GitHub LFS or Git LFS or any of those sorts of things? You're not, because this is a hard question.
Oh no. So it depends generally, right? If it's just a CSV and it's not very, weighty, I could probably just put it on GitHub and then version it that way. Not a big deal. If it's large, trying to find somebody to store large data files is not an easy process. I've been turned down from multiple academic places that store your data set for scientific use. No, they don't. It's a lie. The cake is a lie. Sometimes what you end up doing, at least what's working for me, is when you process the data set, you put the date. Generally, if you almost like you were working on a Scratch template for that day, the date that you are currently on, because you're not going to generally process it more than once a day. And if you do, you can add some more qualifiers on the bottom or at the end. But generally, that's sufficient to keep versioning for me locally.
So it's the old like one, two final, no really final, this sort of thing is what we end up doing. But for scientific
I
data,
used to do that, yes.
No one does that. No one does
No,
that.
I'm okay. I'm okay admitting I used to do that.
I used to do that. I still do, but I used to too. Like,
No, then you start going, all right, so when was the last modified date? You start going like forensic style on it. All right, so how many kilobytes is in this notebook?
So I had one last question. I know we're butting up against time here, but as far as classifiers go and like the algorithms used there, like how is it that what do you end up using, I guess, for the analysis that you do, and why do you pick the different classifiers?
That is the scope of a whole talk.
I realize that. I just was hoping you had like an easy answer for me, but if you don't, that's fine.
No. I can actually answer this one pretty quickly. So I use classifiers, a binary classifier.
Okay.
And because I use that because my labels are 0 and 1. Either it's attack traffic or not attack traffic. In the event that maybe we had different qualifiers, maybe 0 is benign and 1 is insider threat and 2 is malicious attacker and 3 is abnormal, right? Then we would use a different classifier. And then we'd start looking at like multivariate analysis instead of just binary.
Okay, cool. Well, good. I know we're getting ready for the next portion. So Heather, thank you so much. I don't think we have any other questions. Did you guys see any others come in?
I think that's it.
Okay.